Here we go. Communication in the power industry. I'm Alex Trafton. I'm going to spend the next 5 minutes introducing this topic, and then Joe and Maddie will take over. When we think of what makes up our power grid, what comes to mind? Power generation, step-up transformers, high voltage transmission lines, step-down transformers, and the low voltage distribution. Did I forget anything? Yes. Because equally important to what I just mentioned is the communication system. Communication and power system is critical for alarm monitoring, protection relays and controls, voice and data communication, and for the eventual implementation of the smart grid. The smart grid needs a lot of data and more bandwidth for two-way communication, phase measurements, not just the magnitudes, and real-time load data to enable real-time pricing. Now let's talk about communication mediums today. The old school legacy technology includes power line carrier communications, where signals are piggybacked on the power lines. It's the most common. We also have telephone wires where the signals are sent through copper, but they both have low bandwidth capabilities. The more modern wireless technologies that give us a little bit more bandwidth include the radio. You should know what that is. Microwave communications, which is like a narrow beam radio, and satellites. But what most experts agree to as the best option is fiber optic cables, which has the best of everything: high bandwidth, low attenuation, fast data rates. However, it is expensive. But what enables us to use all these options are communication protocols. So I want to talk about communication protocols in general so that you can better follow the explanation of the protocols that Joe and Maddie will talk about later. So when attempting to send and receive data between two places, a lot of questions will naturally arise. Is the receiver ready to receive data? How much data is being sent? Data will be sent by what size chunks? Who's this data for? Who's this data from? Has the data reached the receiver? Is this all the data? Is the data corrupted? So we need to provide data about the data. That's called metadata. So protocols as a word is simply a set of rules to follow. Communication protocols are used in order to answer those questions by organizing and formatting the metadata. So where do you put this metadata? You put it at the beginning of the transmission, of course, at the header. On the left is a conceptual example of a data header. So in this super simplified example, for a fixed beginning length of every message, the binary header will tell you what version of the protocol to follow, what protocol to follow, the total size of the following data, and the maximum number of bytes the sender can send per transmission. In reality, actual headers contain much more information than that. For example, on the right is the data header for Internet Protocol IP, and you can see it answers all those questions and more. Now, this is IP protocol is part of the TCP IP protocol suite. It's part of the suite because specifying how data should be formatted, addressed, transmitted, received, etc., is divided into 4 layers, each with their own protocol. Those layers are the application layer that tells you how to take input from the user and prepare it for transmission, the transport layer that handles the host-to-host communication and opening the connections, the internet layer that packages the data into packets and establishes the routes, and the network access layer that checks for errors as it reconstructs the data from the binary coded packets. Now, the protocol stack to the right of the TCP IP stack is the Open Systems Interconnection, or OSI model, which Joe will bring up again in a minute. But basically, OSI is an older but still widely referenced network layer model that abstracts 7 network layers to accomplish the same thing. So that's the general idea of communication protocols. Now I'll let Joe and Maddie take over to go into the details of 2 protocols used by power systems for relay protection. Joe will talk about Modbus protocol, and then Maddie will talk about mirrored bits protocol. Thank you.
Hi everyone, my name is Joe. I'll be talking about Modbus. Just like how TCP/IP specifies how data is exchanged over the internet, Modbus specifies how signals are transmitted from instrumentation and control devices back to a main controller or data gathering system. Modbus protocol was developed by Modicon Systems in 1979 and has been the power industry's de facto standard for communications between intelligent devices, sensors, meters, and instruments. Also, it is used in communications from field devices to SCADA and human machine interface systems, as well as in remote terminal unit applications. Modbus defines an application layer messaging protocol on the Open Systems Interconnection Model. The OSI model describes how information flows from one application program to another through a network medium. The OSI model subdivides a communication system into several layers, with each layer performing its unique collection of similar functions, providing services to the layer above it and receiving services from the one below. The figure shown demonstrates, for example, data communication using the OSI model between a substation and a central station through a wide area network. The top three layers, the application, presentation, and session layers of the substation and central station communication systems, address the application message sent between stations. The bottom four layers, the transport, network, data link, and physical layers, address the method for the transportation of these messages. Modbus describes the messaging communication dialogue in the application layer of the OSI model. Modbus communicates using a master-slave technique in which only one device, the master, can request data and information or initiate transactions called queries. The other devices, the slaves, respond by supplying the requested data and information to the master or by taking action requested in the query. An example of this is a control center requesting data and information from the numerous substations. In general, there are three versions of the Modbus protocol, and they are Modbus American Standard Code for Information Interchange, or Modbus ASCII, Modbus RTU, and Modbus TCP/IP. Modbus ASCII and Modbus RTU are both used in serial communication. The difference between the two is the format of the communication message. In Modbus ASCII, each 8-bit byte in a message is sent as two ASCII characters. Modbus ASCII, which is human readable and contains more information per ASCII character, is generally used for testing purposes. The advantage of the ASCII format is that it allows time intervals of up to 1 second to occur between characters without causing an error. In Modbus RTU, each 8-bit byte in a message is sent as two 4-bit hexadecimal characters. Modbus RTU is a compact binary representation of the data, which allows more data exchange to occur compared to Modbus ASCII. Modbus RTU is considered simpler than Modbus ASCII, thus it is used more for normal operations. Modbus TCP/IP utilizes the TCP/IP transmission protocol over Ethernet technology. When Modbus information is sent using these protocols, the data is passed to TCP protocol where additional information is attached and given to IP protocol. IP protocol then places the data in a packet and transmits it through the internet. An advantage of Modbus TCP/IP is devices designed with different communication protocols but using Ethernet technology can transmit data to devices using Modbus TCP/IP through Ethernet packets that are formatted to the Modbus protocol. The messages exchange over the Modbus protocol is structured based on the Modbus protocol data unit format, or Modbus PDU format. The structure of the Modbus PDU is displayed on the top right portion of the figure shown. The address field contains the address of the slave device. The function code field indicates to the slave what kind of action to take. The data field provides the slave with additional information required to complete the request specified by the function code. The error check field is filled by Modbus by using various error checking algorithms for reliable transfer of data. The PDU structure is modified for each of the Modbus versions to form their unique Modbus application data unit format as shown in the figure. Each Modbus version requires certain features to provide reliable communication. The ADU format is additional structure information to the PDU and is required in order to exchange messages using the different Modbus versions. Modbus is most suitable for communication with its substations that contain devices meant for protection, control, and metering.
Hey y'all, my name is Madeline Coffrin, and before we talk about mirrored bits, let's take a second to dive into communication and power system protection, and then we'll talk about how mirrored bits applies. So power system protection is a branch of electrical engineering geared towards protecting the power grid from faults. Faults occur when there's an unintentional path to ground or two or more lines touch, creating a current surge. Current surges can damage utility equipment such as generators and transformers, or it can damage customer appliances, both big and small. And so it's really important that we isolate these faults in order to minimize the amount of damages. Now, not only do we want to isolate the faults, but we want to stabilize the grid when doing so. It would be great if we could just isolate the fault and get rid of power everywhere, but then we wouldn't be providing a service to our customers. So we need to be able to isolate that faulted location and keep as many customers online as possible. So basically minimize the amount of outages for our customers. So in order to detect, react, and isolate these faulted locations, communication is key. So Modbus and TCP/IP communication are the current standard for most companies. There's a couple other ones that are used, and we'll talk about that in the next slide. However, Modbus and TCP/IP are the main ones we focus on in this presentation. So these current communication standards have a low data rate, but there's also a high probability that data can be transmitted wrong or lost in collision. And so this causes a need to resend information, creating a lag. So not only is there the possibility that we're sending the wrong information, but we're increasing the amount of time it's taking to transmit the correct information. And so we have that possibility of wrong information being sent and an increase in time. And so that really isn't all that great or beneficial for what we are looking for as power protection engineers. And so SEL came up with this newer type of communication called mirrored bits. So if we look at this picture, I really enjoyed this picture because it was a great comparison of multiple different vendors and manufacturers, their types of relay protections, and the communication methods that they use for it. And so we see that a lot of them still use that Modbus TCP/IP communication here and here, but we also see that mirror bits is only used through SEL. So mirrored bits was created by Schweitzer Engineering Laboratories as an innovative, low-cost, high-speed, and secure communication method that sends relay-to-relay status information through digital messages. So what that means is one relay is receiving bits that follow or mirror the status of the transmitted bits sent from another relay. So over here we have this picture where we see relay 2 is receiving bits from relay 1, and it is directly mirroring the value that is being transmitted. So there's some pros and cons that come with every type of communication method, but there's a lot of really great things about mirrored bits that make it very beneficial for protection engineering, such as the high-speed communication, which allows information to be transmitted at protection speeds. So for a lot of breakers, circuit breakers that communicate with our relays, and protect and isolate those faulted locations, they operate in 3 to 4 cycles. So a cycle is 16.67 milliseconds. So that means that this communication and action needs to happen in less than a minute, or less than a second, excuse me. So it is happening very, very quickly, right? Each cycle is 16.67 milliseconds. We're fitting 3 of those in. It's happening fast, which means our communication has to be very fast. But not only does it have to be fast, it has to be accurate as well. We have to be able to send the correct information. And so mirrored bits has multiple security methods put in place to ensure correct bit transmission, such as bits are being triple checked for consistency, bytes are checked for parity, framing, and overrun errors. There's loopback detection, and at least 1 message is received for every 3 messages sent. And so mirrored bits are very dependable because of these security features. And it's important for a power utility so that they can provide that safe and reliable service to their customers, which is the #1 priority. So there are some drawbacks to mirrored bits as well, such as the narrow bandwidth. And although this narrow bandwidth works great for power protection, it isn't great when you're going to things such as SCADA, which require a larger bandwidth in order to transmit the information needed. So in conclusion, power utilities are moving in the direction of smart grids, but in order to do this, we have to have the correct communication devices necessary for that proper transmission of information. So the goal for all utilities is creating that safe and reliable network, and in order to do so, communication is an essential component in delivering the best possible service to its community and its customers. Thanks.